Welcome to 5-10, the last lesson in Chapter 5. Congratulations. I hope everything's going well with you. We're going to wrap this up with similar figures and this idea of a ratio of similitude, which is your vocabulary word for this. When we talk about ratios, we're talking about how are things proportionally compared. We're looking at this drawing below about the proportions for an infant versus an adult. We can realize that these ratios of the head to the other parts of the body are quite different than in a child, in a baby, than they are in an adult, and so that our bodies then are quite different. There are other animals like the elephants in the other picture that in fact the babies are quite proportional to the adults in terms of their shape. They just get bigger as they get older. They don't change their proportions. We're going to take a look at this idea of similar figures. When we say they are similar, it is not to say they are exactly the same, but it's to say that the proportions are the same. If it has angles in it, if it's a polygon, the angles will have the same angle measure. The ratio of the lengths of the sides will be equal. So the corresponding sides, of course. Let's take a look at what that might mean. If we see here in the coffee pot activity, pictured it right as a coffee maker, and it's 12.5 inches tall, 5.625 inches wide. Well, that's the actual height. Now we're looking to see what is the height and width of the coffee maker in the picture. Well, we know that the actual height is AB, or is from A to B, is the pictured height. The actual height, we know that's 12.5 inches, right? So we're going to find that if we do a measurement of this, that the height is AB to CD and find the height and width of the coffee maker. So we've got to measure those. So we measure AB, and AB, you should get that that's about 2.5 inches. So try measuring that. And then you take the width, and the width, that's from C to D, and I'm getting that that's about 1 1/8 inch. So you've got those two things, and now we can calculate the ratios of this. So the ratio of the height in the coffee pot to the actual height is going to be about 0.2. The width divided by the actual width, which is 1 1/8 divided by 5.625, is about 0.2. And we're going to find that these ratios are about equal to each other, which is what we should get if they are similar. We measure EF, which is the height of the coffee pot, and then it asks you to solve a proportion to find the actual height of the coffee pot. Well, if you measure it, you're going to get that it's about 13/16. So solve a proportion to find that. So 13/16 is to one of the other picture values. So 13/16 is to 2.5, as the actual coffee pot height, X, is to 12.5. So that would give us what we would need to do this calculation, and you'd get that it'd be about 4 1/16 inch. So that's solving a proportion to find an unknown value based on measurements and calculations. Leads us to our fundamental property of similar figures. If two polygons are similar, then ratios of corresponding lengths are equal, and corresponding angles have the same measure. This is called the ratio of the lengths of corresponding sides of two similar figures is called the ratio of similitude. So let's see what we can do to find lengths of similar figures. Now here we have an example 1. Our African element can be 30 feet long and 11 feet high at the shoulder. Estimate the length of a baby elephant that is 3 feet high at the shoulder. So here we're going to just create our relationships. The height of the adult divided by the height of the baby. is equal to the length of the adult divided by the length of the baby. Now, could we have set this up differently? Sure. This gives us something we can work with. We'll solve for x. So the height of the adult we know is 11. The height of the baby we know is 3. The length of the adult we know is 30. Length of the baby is our unknown. We're trying to find that. That's x. We use the means extreme property here. So we go from 11/3 equals 30 over x to 11 times x equals 90. Divide both sides by 11, so x equals 90 over 11, or approximately 8.2. So the baby elephant is slightly over 8 feet long. Okay, they're similar. So since they're similar, we can use this ratio of similitude. Guided example 2. In this one, we have the two quadrilaterals at right are similar, which means that their angles are equal and their sides are proportional to each other. So corresponding sides are proportional. The side corresponding to the unknown length CD is which side in the similar. So we have BCDA, or ABCD, and JKLM. And so since we're looking for CD, these are oriented in the same way that's convenient. We can see that LM is the side that is the corresponding side to CD. And so there's a pair of corresponding sides whose lengths are both known. And for those, that would be BC and KL are both known sides. So we know that these CD is to LM. So the side CD, X, is to LM as, and we want to keep this together. Since I use CD here, it'll be BC is to KL, goes right here. So CD is to LM as BC is to KL. Now we do our substitution. X is our unknown. LM is 12.6, BC is 3, and KL is 4.8. Now we use the means extreme property. We get 12.6 times x equals, 4.8 times x is equal to 3 times 12.6. We divide by 4.8, and we get that x is equal to 7.87. So we can use this type of information and the corresponding parts to determine the unknown. And it's the idea that in similar figures, their ratios are the same. Now here in example 3, this one's interesting because you're going to be doing something like this in Death Valley. Or on one of our biome trips if it's not a Death Valley trip, where we're using measurements to find out about things that are unknown to us. And this is this idea of similar triangles. Give me a second, I'm going to bring up a little something else. Okay, here we are with 5-9. And I want to go through this idea of similar triangles. And we can use this to help us when we're measuring things in the field, but let's just get the basic idea here. So if I have two triangles that are similar, and I'm going to go ahead and label these, it's good to put some kind of lettering on the vertices so that we know what's what here. Let's see. And we're going to make this a right angle here. So I've got a few things. Let's see, we've got an unknown length here. We've got a known length here, and we'll make that in inches. We have another known length here. And for this one, we've got a known length here. So we've got our two triangles. We're saying that they are similar, and we want to find out what is the length of x. Well, since they're similar, it means the ratio of sides are equal to each other. So we have two ways we could go at this. So let's look at way one, and that is that x is to 5 as, so x is to 5, what side corresponds to side x? Well, that's the side D, our 4-inch side. And so that's 4 inches, and 5 corresponds to 3, as 4 is to 3. So we now have a ratio that we can use. From that we solve for x. We could use the means extreme property, but it doesn't make a lot of sense in that all I need to do is multiply both sides by 5. If I do that, I get that x equals 5 times 4 is 20 over 3. And that's my solution, 20/3 inches. If I'm really needed to, I could say that that is approximately equal to 6.7 inches. I said there were two ways, so let's look at way 2. In this case, I took the ratio of x, the unknown side, to a known side from the same triangle. I could also go with the corresponding sides. X is to 4 inches as 5 inches is to 3 inches. So the first triangle divided by the second triangle side. First triangle side divided by the second triangle side. I then, again, means extreme property doesn't help me here. I just multiply by 4. 4 times 5 is 20. And that will give me that 20 divided by 3, which was approximately 6.7. There's our solution. So this is the idea of using a ratio to determine these two things. Now when we look at the next example, in that one we have example 3. It said use the measurements from the right to find the height of the flagpole. So what we would do is we would create a small triangle that we could handle and line it up so that it fit within a triangle that was established between us and this height we're going to be measuring. Now, see me in class. We're going to be going through this before we go to Death Valley in 2015. We'll go through it again in others. But if you're wondering about how to do it, come see me, where you can create a similar triangle, use it to find out an unknown height, like the height of a flagpole that you can't actually measure. Much like we did in the other case, the unknown height was h. In this case, we used corresponding sides. 3, the known height of our triangle, is to the unknown height h, as our known length of our triangle 5 is to our known length to the flagpole's base, which is 72. It's a right triangle, you notice, so they are similar triangles, and we using means extreme property and a little bit of manipulation, we get that 5h is to 72 times 3. So 5h equals 216. We do our division by 5 and we get that h is equal to 43.2 feet, or about 43 feet tall. That's using the similar triangles. Well, that's it for chapter 5. Best of luck in going through this stuff. Good luck on the mastery quiz. If you have questions, you need more examples, I am delighted to go through that with you in class. Come see me about it, and good luck on the test. Best of luck. Bye.